Technology. It makes us think of numbers, data, analytics, and math. All the stuff that goes on in our head. But the truth is, the head is powerless when it's not fueled by the heart. And memory is the heart of technology, the driving force that pumps life into every product, application, and innovation it touches. Memory is the heart of science, allowing researchers to explore the microscopic detail of the human body and the infinite grandness of the universe. Memory is the heart of industry, making precision agriculture more productive, vehicles more autonomous, and smart homes more convenient. It is the heart of consumer experiences, making esports more active and VR more interactive. And it is the heart of AI, enabling it to do everything from make us coffee to make us laugh. At Micron, accelerating intelligence is more than a science. It's a passion, which is why we've assembled more than 37,000 thinkers and doers in over 18 countries who know that innovative memory solutions are essential to our future. A promise to continue pushing the limits, shaping the way we live, the way we work, the way we see the world. Memory is at the heart of what makes the impossible possible. And we are the memory makers. Micron, intelligence accelerated.
India is growing. In this changing India, design and manufacturing in semiconductors and electronics are important activities to boost its economy and meeting local consumption while being globally competent. Government of Karnataka, K-Tech and IESA together formed Semiconductor Fabless Accelerator Lab, a K-Tech Center of Excellence for Fabless, an initiative for developing and strengthening the fabless ecosystem in India. SAFL focuses on companies in semiconductor domain with their abilities to work on ICs and IPs. SAFL provides full access to expensive EDA and other tools and limited support towards MPW silicon tapeouts. SAFL also helps in mentoring, aggregated partner offerings, raising funds, aligning go-to-market strategies and various needs. SAFL initiative is much in line with the overall goal of Atmanirbhar Bharat. Potential in semiconductor industry is huge and SAFL helps explore the best of the possibilities. Located at MG Road, Shuffle is easily accessible to all. Apply to Shuffle program all round the year. Come, let's explore.
Good morning, my dear friends, and good evening to the participants from the other time zone, and good afternoon to the participant from the Japan time zone. So, Preet Yadav. My name is Preet Yadav. I'm organizing co-chair for this conference. I welcome you all to the second day of the conference. And effectively, we can call it fourth day because we had tutorials during the first 2 days of the conference. So, let me take a pause here and quickly brief you about the what all is going on in the background for this conference. I know I'm sitting between you and our distinguished speaker, Professor Umesh, who you can already see on the screen. So this conference being run as virtual show, we have created 4 satellite centers to run this particular conference. One at IIT Guwahati and IIT Roorkee each. One at IESA, Bangalore, and the 4th at NXT Semiconductors here in Noida, from where I'm hosting this session. So we tried to, do the functional safety analysis as we do for all of our chips. So we created a backup of backup. So we have, these 4 satellite centers supporting each other, though we have redundancy within the same center, but if one goes down, the other would pick up and vice versa. So a lot of thought process, logistics, and I would say deep dive has been done to bring this show live to you. So without taking much time, I would like to get started with our D-Day. So I would request admin to bring up the files. Next one, please. So this is the agenda for the day. We started the day with 3 parallel tracks, and now we'll be inaugurating the day with a keynote talk by Professor Umesh K. Mishra, followed by a very interesting involved panel discussion. And then we'll break for SRF UDT sessions. We'll have again 2 keynote talks, then lunch and post lunch talks, and finally we'll conclude with the award ceremony in the evening. Next one, please. So again, let me take this opportunity to thank all of our sponsors to make this show, happening actually this D-Day. I would like to thank to our technical sponsors as well. Next one, please. So these set of technical sponsors are always with us all these years, and special thanks goes to our collaboration partners, Ministry of Electronics and IT, IIT Guwahati and Roorkee, IESA and TechSagar, and DAC, our sister conference. Next one, please. I just quickly want to make you aware that this year the conference is virtual, and so do the exhibitions. So we are calling this as Virtual Product Showcase. It's on the conference website. If you go to events and click on Virtual Product Showcase, you'll be able to see a good product showcase put together by all of the sponsors and our partners, as you can see on the screen. Next one, please. Let me take this opportunity to again welcome our all distinguished speakers for the day. As I said, we'll start with Professor Umesh K. Mishra and followed up by the other keynotes and panelists during the day today. Next one, please. Okay, so here we are, bang on the time. Let me take this opportunity to welcome Professor Umesh K. Mishra for this inaugural day of second day of the conference to share his view on GAN electronics, the next generation platform solution from power conversion to wave communication. So GAN is the new buzzword in this, we call it Silicon Valley, and Professor Mishra, I'm waiting for the Neuro Valley to be born with, your strong research and, I would say practical products in the market now. So let me introduce Professor Mishra, though he don't need any introduction. Professor Mishra, he's a distinguished professor, University of California. He's Donald W. Witter Professor of Electrical and Computer Engineering at UC Santa Barbara. He received his BTech from IIT Kanpur, then MS from Lincoln University, Pelham, PhD in 1984 from Cornell University, New York. He has supervised 70 plus PhD theses in his tenure, and 40 of them are on GAN. I don't think so there's any other person on this earth with 40 PhD supervision in GAN area. We're glad sir you're with us today. He has 1,000 plus papers and 100 plus patents. His students have demonstrated the first microwave power amplifier in GAN. He co-founded Transmorph in 2007 to commercialize GAN on silicon transistor for power conversion, where he serves as chairman and CTO. He has multiple awards, distinguished awards on his name. He received the ISCS Young Scientist Award for his work in GAN. Thereafter, he received IEEE David Surfoff Award, ICS Walker Medal Award, ISCS Quantum Device Award, and whatnot. He also received IEEE MTT Society Distinguished Educator Award in 2016 and the Faculty Research Lecture Recognition, the highest award to a faculty member by the UCSB Academia Senate in 2018. He is Fellow of IEEE, an International Fellow on the Japanese Society of Applied Physics, fellow of National Academy of Inventors, and a member of the National Academy of Engineering. So with this, I welcome Professor Mishra to come and share his thoughts on what's new or what's next in GAN. Welcome, sir.
Okay, thank you very much for the kind introduction, Preet. I'm here to talk about gallium nitride electronics. So I just wanted to let you know right from the beginning that I'm an evangelist of gallium nitride. So I'll be talking about, I'll be delivering my thoughts about gallium nitride. 90% of it will be true, 10% will be exaggeration. Okay, so this is basically, I believe that it's the next semiconductor that can stay alongside silicon as far as a really important semiconductor. Every semiconductor technology has to be high performance based on application. It has to be very reliable. That's very important. It has to have a roadmap for lower cost with every generation. Otherwise, it will not have widespread impact. And for low cost, you require very wide market penetration. If you have a niche semiconductor, it'll be very useful, but it'll remain at a high cost. And I believe that gallium nitride, more than any other semiconductor, satisfies all these requirements. Of course, other than silicon. Silicon is the granddaddy of everything. So if you look photonics applications, LED and lasers, which we see every day, and I'll talk a little about that. Electronic applications, the basis of my talk, which includes wireless base stations, radar, millimeter wave communications, and so on and so forth. Sensing applications, extreme electronics. I won't be talking about that too much, but ex-students of mine like Shravanta Chaudhary at Stanford and others are working on things like diamond and GAN and co-integration. So let's look at let's take a first look at photonics, right? So these are colleagues of mine, Shuji Nakamura, Steve Denbach, Jim Speck, Stasa Keller, so on and so forth, and their work. So LEDs have become everywhere, right? They're everywhere. They're omnipresent. And basically, if you look at the oil lamp, it was 0.1 lumens per watt. And today, the LED is close to 300 lumens per watt. This has completely revolutionized lighting and also made it safe. We don't need fluorescent lamps, which are mercury-based anymore, okay? And what has also happened is that it has basically taken decorative lighting, made it possible, automotive lighting, LEDs in cars, agriculture, I'll talk about in the next slide, displays for phones, indoor lighting, and so on and so forth. This is going to be a very big deal going forward. And the reason I'm giving you a photonics part of the lecture is because I want to, the reason I'm talking about this is this very big gallium nitride ecosystem, which is beyond electronics, which will help to drive the cost down for the gallium nitride material system. So here is an LED plant factory, which is basically where people are growing plants using LEDs and just very little water. In India, which is going to become water stressed in the future, you can basically have plants like this in Rajasthan and it not be a big issue. So this is going to be huge going forward. Only 1% of the water will be used compared to outside. This is going to drive GAN. Lasers are going to go into automotive cars as headlights because you can get a 1 kilometer throw of the light compared to 200 meters with an LED. And of course, augmented reality with micro LEDs are coming on. Big wall TVs, UV LED, water sterilization, and of course, solar powered lighting for the third world and others. Laser cinema in Santa Barbara, now in California. There's a theater that has laser projected cinema, which is unbelievable to look at. And one has to really look forward to Li-Fi networks. This is basically modulated light using gallium nitride. So your light bulb itself, your light bulb itself becomes your part of your wireless network. So the world is going to change, and a lot of it is going to be driven by gallium nitride. Now, there are two forms of gallium nitride. One is called gallium polar, and the other is called nitrogen polar gallium nitride. Gallium polar nitride has gallium face, which means if you look down on the crystal from the top, you'll see gallium, Nitrogen polar, if you look down on the crystal from the top, you see nitrogen. Both of these are very important, and I'll talk to both of them in a minute. Okay. So why is gallium nitride so remarkable? It's very remarkable because the material is actually not very pure to look at. In fact, it's full of dislocations. So the material is grown actually on, say, silicon or sapphire or some other foreign substrate, and it is full of dislocations. It looks really bad because it actually is a defective material. But independent of that, it puts out light, which is amazing. It's the only semiconductor which is so dislocated that actually puts out light. And such a dislocated material has displaced silicon carbide MESFETs in military radars. So in the US, the DoD has announced that the next generation radar on ships is going to be all gallium nitride. Okay, and when we started this work at Santa Barbara in 1993-94, I would have never thought that it would be in ships in the early 20s, which is going to happen. So let's first talk about power conversion, okay? And the biggest, one big problem right now that we are seeing is that power, of all the power that is generated in the US, 10% is lost due to conversion. That is, just converting electricity from the form that it arrives in your socket, in your power outlet, or your plug point, as we say in India, to the actual appliance. So that conversion, like the adapter for your laptop, if you sum all such conversions, 10% of the power that we generate gets lost in these conversions. It's enormous. $40 billion in economic cost per year. You can call it's a hidden tax on electricity. So let's compare gallium nitride and silicon carbide. There's a thing called, of course, we all know there's electron mobility, and gallium nitride has an electron mobility of 2,000. This material has a band gap of 3.4 volts, which means it's almost like an insulator as far as the band gap is concerned. Relative to silicon, it's more than 3 times the band gap, but the mobility simultaneously is more than twice that of silicon. This combination of high band gap and high mobility makes it an amazing transistor. So the high breakdown field holds high voltage like an insulator, but the high mobility gives you low resistance like a metal. And the transistor we use is called an aluminum gallium nitride, high electron mobility transistor. It actually looks very much like a silicon MOSFET. So if you look at a silicon MOSFET, this is silicon dioxide. Replace silicon dioxide with aluminum gallium nitride. Replace silicon with gallium nitride. And lo and behold, you have an inversion layer in silicon, and you have what we call a two-dimensional electron gas in gallium nitride. So these devices are very equivalent, okay? The only difference is that the electrons in gallium nitride move 50 times faster than an inversion layer electron in silicon. So this gives us opportunities in power switching, power conversion, like I talked about, and very high frequency as well. So let's give you a small thought about how much power we waste. In industrial motor drives, I'm not talking about only robots, but all industrial motor drives, we waste about 207 terawatt hours. In data server power supplies, over 52 terawatt hours per year is lost in just these conversion processes, just converting AC to DC, DC to DC, and so on and so forth. Solar inverters, this is going up like crazy. This is an older slide. This is much more than 5 terawatt hours now. And electric motor inverters for car. And of course, this depends on the number of cars in the market, and that's growing exponentially. So how much is a terawatt hour, right? And so the amount of energy consumed in San Francisco is about 6 terawatt hours, New York City about 50. Las Vegas, just that little city, consumes 33 terawatt hours because of all the casinos over there. So the amount of savings potential in GaN, actually, if you total it up, is over 300 terawatt hours, more than the entire consumption of electricity on the west coast of the United States. So this gives you just a scope of the problem and how much we can impact it. So the key to mass adoption is low cost, okay? I mean, if you can't drop the price I think you're living in a fool's universe in trying to sell stuff. And the number one thing what one realizes, big stuff costs more. The bigger the stuff, more expensive it is. So the most important thing to make things less expensive is you make things smaller. Okay, electronics is made of transistor, passive elements, and heat sinks. Transistors, they're small but expensive, use fewer of them. So use circuits that don't demand so many transistors. I'm talking about gallium nitride. In the case of silicon, silicon transistors are free, so you use as much as possible. We go the other way, we use as few as possible because the transistor is still expensive. Passive elements are very expensive. They're large, and they decrease with frequency. So you want to use fewer transistor, but at higher frequencies so that the passive elements shrink and the cost comes down. And lastly, you want it to be very, very efficient because heat sinks and stuff like this are what take up a lot of space and are very expensive. You're buying a chunk of aluminum. Aluminum is expensive, much more expensive than gallium nitride. So you want to basically make few devices that can do the function at high frequencies with minimum waste of heat. And an example of this where small stuff becomes better is think about the old days when we had a C-band antenna, which is 4 to 8 gigahertz, trying to connect to the satellite. You could see this outside LRDE or some other establishment like that in Bangalore, but you wouldn't see it outside everybody's house because it wouldn't fit in anybody's house. And people who had expensive homes would not buy it because it's too damn ugly. So what ended up happening is, but from 4 to 12 gigahertz, we shrunk the antenna, everything became smaller. You could handle it by one person could go and put it in your house. All of a sudden it became cheap. So and now everybody has a direct TV or some kind of a direct link to for TV, okay? So there's a Moore's law for power electronics, very different from Moore's law for VLSI. And the Moore's law here is we do not shrink the gate length, okay? Here the gate lengths in power electronics are all in the micron range, okay? We are in 1970s as far as all of you are concerned, as far as lithography is concerned. But what we do is we make what is the Moore's law? The y-axis is output power density. How much power can we convert per centimeter cube? This is making stuff smaller, okay? More conversion in a smaller space, smaller volume. So the way that is imagined and actually delivered in power electronics is basically just inventing devices. So you go from silicon rectifiers to bipolar transistors to insulated gate bipolar transistors to silicon superjunction devices, silicon carbide GaN, so on and so forth. So you actually change materials and devices. That's how you go up in the Moore's law. We don't shrink gate lengths to that great extent. So what I'm going to do is I'm going to take a little bit of examples from Transform, the company that I founded 14 years ago. In fact, today is the 14th birthday of Transform. And I'll give you some market examples to see how this works. So today, gallium nitride solutions for adapters are becoming very, very popular. Okay, not only Transform, other companies like Navitas and Power Integrations are all selling solutions for GaN adapters. Why? Because it all basically is they're ultra slim and lightweight. Why? They can convert significant amounts of power, 65 watts, 75 watts, 150 watts. These are significant amounts of power in a very small form factor. This is what gallium nitride can do. So it's just taking off like a rocket ship at the moment, okay? This kind of a hockey stick, as we say in America, this hockey stick actually occurred last year and has gone gangbusters, okay? So this is the first one. These are adapters for phones, laptops, iMacs, so on and so forth, iPads. Gaming is another very big area where efficient power supplies is important because gaming is a very energy intensive. I mean, Bitcoin mining is a very intensive exercise. And here, every dollar you waste in heat is a Bitcoin dollar that you cannot generate. So here, gallium nitride power supplies are finding a tremendous market because Bitcoin mining is becoming extremely important. And this is an example of transforms devices in a company called Corsair, where without changing the price of the part, you could actually get a much smaller box. Why? Because the silicon solution has all silicon, but a lot of other parts like inductors, filters, diodes, so on and so forth. And gallium nitride solution has 2 gallium nitride FETs and a cap. So this makes it cheaper than the silicon solution. Okay. Okay. Bell Power has come out with a family of data centers. This is basically basically for titanium class power supplies. The European Union is putting in a standard which is greater than 98% power supply efficiencies, and gallium nitride is trying to address those issues. The fundamental gallium nitride advantage is in its building block. All power conversion not all power conversion, that's an exaggeration. A lot of power conversion going forward is going to be built on what is called a half bridge. Basically, 2 gallium nitride FETs in series like this, much like you would see in a CMOS. Only thing is this is all unipolar, and this is called a high side, this is called a low side transistor. This is connected to high voltage, typically 600 volts, 1000 volts. And basically you have different structures like what's called a totem pole, which is a hard switched, isolated, phase shifted, full bridge. Don't worry about all this. But all I want to say is that there are multiple circuits that do the power conversion. And this particular circuit goes from AC to DC directly without using any rectifiers, okay? And this is actually a huge advantage for gallium nitride. This is where a big advantage is happening in PFC. And for lack of time, what I'm going to go ahead and say is, let's just compare various technologies. Here's a comparison of a gallium nitride FET and a silicon carbide FET, both having an on resistance of 35 milliohms. And what we're looking at are both of them in this totem pole configuration. And you can see that the gallium nitride efficiencies and the silicon carbide efficiencies are shown here. And the gallium nitride efficiency is 20% higher, a 20% reduction in power loss compared to silicon carbide. Remember, you might think there's no difference between 99% and 99.2%. It's a lot of power that you have to take out when you're trying to deal with 6 kilowatts or 7 kilowatts of power. And as a comparison, here's a comparison of all transistors today. This is all the same, effectively the same resistance transistors, and you can see that the gallium nitride transistor, even though it's on silicon, gallium nitride on silicon transistors can perform better than silicon carbide MOSFETs or silicon carbide JFETs. This is kind of new data, okay, it's just coming out. In fact, you guys are seeing it for the first time. We haven't shared it before. It says that it's very important to actually look at power conversion and application, and it's my prediction and hope, maybe hope more than prediction, that gallium nitride is going to show that it'll outperform silicon carbide in many applications at a much lower cost. Okay, the next big market is electric transportation. I'm not going to talk too much about it, but where gallium nitride is playing a role is in various things like emergency preparedness. This is a DC to AC inverter that's going to be in every car. There's an AC to DC onboard charger. There's DC to DC converters. Where gallium nitride is not there today, where silicon carbide is penetrating, is in the main inverter that drives the car. But gallium nitride, we are working hard at it, but we are behind silicon carbide in this domain. So last few slides, I'll talk about millimeter wave gap. Millimeter wave GaN that we have pursued, we did a lot of work in gallium polar, and that's now in the market at the university. About 10 years ago, we decided to pursue this nitrogen polar GaN, which is basically gallium nitride flipped over. And people didn't think that this would work. And I'm glad they didn't, because nobody else worked on it. And I was peacefully doing my research with no competition, which is always a very good thing to be. And so what ends up happening is that the most important thing for RF is you need very high velocity so that you can carry the current. You need high charge because you can carry a large current. And simultaneously, you need high breakdown field so that you can get large voltages. Gallium nitride has many applications, right? Right from radar systems to SATCOM to base stations today. All base stations in 5G are switching over to GaN. And the reason is aluminum, from the time we demonstrated microwave power at UC Santa Barbara in 96, aluminum gallium nitride HEMS has taken off like this in performance. So when anything like this happens over a very short period of time, in literally a decade, then it means that Mother Nature is on your side. So industry has done a magnificent job, and now they have penetrated the 5G market, which is a huge market, and it's along with the military market. So basically, right now, the wireless infrastructure is about 55% of the market share of gallium nitride. Defense is about 36%, and now the pie is just growing very rapidly. But millimeter wave applications are coming on, and I'd like to just last 5 minutes. And the main reason is that 5G is over here, but now bands are opening up for 30 gigahertz communications and higher. And this is all in the millimeter wave domain. And this is all SATCOM. And one of the things I'd like to say is that at 94 gigahertz, which is an extreme, gallium polar, traditional gallium nitride has not done much. And in fact, work done by Raytheon, here's an example of a 95 gigahertz 7 kilowatt amplifier. This is for radar purposes. You can see it had 8,000 ICs and it's lifted by a crane. This is not very useful. So by using nitrogen polar gallium nitride, and I'm going to rush through this, and this is an example of the device, and I don't have time to get into the details, so let me just tell you what really happens. With nitrogen polar GaN, when gallium polar GaN was just stuck here, this invention that we made at UCSB allowed us to get to 8 watts per millimeter instead of 2 watts per millimeter, a factor of 3 to 4 in power density by just flipping the technology on its head. So I'm actually very proud of this work. The US government is funding this now at significant levels, because you can now get very high efficiencies at 94 gigahertz, unheard of efficiencies with 8 watts per millimeter, unheard of power density. But more importantly, it also works at SATCOM, at the 5G areas. Okay, so it also has a commercial play, because 30 gigahertz satellite communication is where lots of people are, including like Amazon for their satellites and so on and so forth, for spreading the internet using satellites. So what I'd like to do is just conclude. Gallium nitride is going to become a dominant semiconductor. I hope I showed you this, because the GaN lighting industry is growing exponentially. The RF industry is now growing rapidly and will grow exponentially with 5G. The power conversion market using GaN is just starting. Like I told you, a few things have started and now it's going to grow. GaN on silicon gives a pathway to very low cost devices. So right now we grow on 6-inch silicon, we're going to 8-inch silicon. So that will drive the cost down. There are new markets starting up. And so I'd like to I hope I've given you a feel in 25 5 minutes plus, that there is a tremendous future for gallium nitride, and I'm glad that there is a drive not only in the US but the world over to make this a mainstream technology. Thank you very much.
Thank you, Dr. Umesh Mishra, for sharing your deep insights about GAN, and which is a buzzword. And as I said, we have Silicon Valley, and I'm looking for the GAN Valley. Yeah. So with this interesting and I would say very catchy topic, I have list of questions, but in the interest of time, I'll try to summarize. So there's multiple questions which came around. I'm just summarizing most of them. Like it was silicon, then we talked about silicon carbide and GAN. What is the fourth or fifth element you see? I know GAN is there, but what next you foresee, which probably would be, talk of topic maybe 10 years down the line?
That's a very hard question, because I think that people have asked me this question, and I think it's just more GAN. It's the same thing, because there'll be new forms of GAN, which people have. In fact, there's an NSF workshop, National Science Foundation workshop, which has exactly this question, and I'm going to participate in it next week. And on the panel, why I'm giving you an early look, my thought is it's just more GAN. If you think about silicon in 1970 was silicon, and then you got silicon germanium, and then you got strained silicon, and then you got FinFETs, and then you got all kinds of stuff. So if you stay with silicon, is it still silicon? I don't know, because it's like strained, it's silicon germanium, it's bi-CMOS, it's this, that. So I believe what is going to happen with GAN is it's just going to get pushed for the next. I've told my students this, I hope I'm not lying to them, that they can retire on GAN. Forget me retiring on GAN. It's got that much of a long life ahead.
Oh, great. Thank you so much, sir, for your passion about GAN. And as I said, I don't see anyone else, at least to my best knowledge, having 40 PhDs, guided under him in GAN area. So thanks for being the revolutionary in this domain. So with this, I would like to, admin to bring up the token of thanks, virtual token of thanks for Professor Mishra.
Thank you very much. It was a pleasure and an honor.
Thanks, sir. It was our true pleasure and honor to host you here. Thank you.
Thank you.
Okay, so with this, I would like to introduce the next session of ours. Admin, I would request admin to bring up the files. Okay, so we were holding back our breath, all these since this morning for this exciting, session of today. The vibrant panel discussion, I would say, seeing all the great faces on the screen about self-reliance in semiconductor for AI, and it's obviously in context to India, but with a global learning, I would call. So AI/ML is becoming a integral part of our critical applications, be it healthcare, medical, transportation, industrial, and whatnot. So the panel here would deliberate on this state-of-art technologies and how our technologists in India they can create this self-reliance in this particular domain. So with this, I would introduce the moderator of this panel, and I'll request Subhashish to Professor Subhashish Mitra to come on stage, and he'll take it forward, introducing for rest of the panel. So Professor Subhashish Mitra, as he don't need any introduction, but let me briefly introduce him. So Professor Mitra, he is Professor of Electrical Engineering and Computer Science at Stanford University. Yeah. So at Stanford University, he directs the Stanford Robust System Group. He leads the computation focus area of the Stanford System X Alliance. He's member of a Wu Tsai Neuroscience Institute. Professor Mitra also holds Carton Chair of Excellence in Nanosystem at CEA Lati in France. His research range across robust computing, nanosystems, electronic design automation, and neuroscience. Results from his research group have influenced almost every contemporary electronic systems and have inspired significant government and research initiatives in multiple countries. Professor Mitra also has a major consulting engagements with Cisco, Google, Intel, Samsung, Xilinx, and whatnot. With his students and collaborators, he demonstrated the first carbon nanotube computers.
You don't have to read out all that, okay?
I just can't hold back,
I think we can start the panel, okay?
Okay, so with this, over to Professor Mitra and all of the panelists. Over to you. And he gave me a responsibility with the buzz, so I'll make sure I give you those smart beeps if we are not doing
right. We are going to cut off people, right, if they go over time, right? That's the idea. Hi, everybody. Good morning. It's morning in India, right? So Good morning, everybody. So welcome to our panel on AI overall. So the best thing for a panel is to be a panel moderator when you have fantastic panelists, right? You don't have to do anything, right? The panelists are going to do their job. And so our job was to recruit the best panelists you ever can. So we have 4 fantastic panelists. The first panelist is my colleague, Professor Boris Morman, who is Professor of Electrical Engineering at Stanford. Boris's research interests are in mixed signal integrated circuit design with special emphasis on sensor interfaces, data converters, and custom circuits for machine learning. Boris has received numerous awards, had been the technical program chair of ISSCC, and is the founding faculty co-director of the Stanford System X Alliance, and he's a fellow of the IEEE. Boris, welcome. Our next panelist is Kaushik Raghavan. He's an AI ML leader and a data science enthusiast. He is with Micron currently, and previously he had held positions in many companies, including Applied Materials, and has successfully delivered ML products across the semiconductor business spectrum. Our third panelist is Sanjay Churiwala. He has a BTech in electronics and communications engineering from IIT Kharagpur and has over 25 years of experience in EDA and VLSI. He's currently a senior director at Xilinx Hyderabad. And our final panelist is Sambit Sahu. He is the vice president of the IoT group and general manager of the high velocity silicon and platform engineering group across the globe at Intel. Previously, Sambit held positions at Qualcomm, Sun Microsystems, and Procket Networks. So, with these panelists, you couldn't go wrong, right? So we will start off the panel, and each panelist will have 5 minutes. That's where Preet is going to keep the time, and in 5 minutes they're going to make their panel statements. So Boris, you go first.
Thanks so much for this nice introduction, Subhashish. So I'm, of course, special on this panel because I'm the only non-digital guy, I think. So it's my honor to be bashing the digital folks.
You're the only non-Indian guy, too.
That's right. But I bet this conference has quite a few mixed signal people like myself. And so I want to sort of give my perspective as an outsider, more or less. So for most of my career, I have actually been working on wireless, wireline type systems. And about 7-8 years ago, when really we saw that this AI ML thing is emerging, I also got sucked into this and became interested in efficient computing. And what I want to share with you is some of the learnings of these 7-8 years in my position statement. Specifically, I want to highlight the differences between these two domains. So for once, if you're like me and you work on these older type systems, wireless, wireline communications, and so on, the abstraction levels actually provide a very good shield to you. Someone designs a system and then they tell you, hey, I need an ADC that has 10-bit resolution and runs at 100 megahertz, and you're good to go. You don't even need to know what OFDM is. You don't need to know any of this stuff, and you're just fine. On the other hand, what I found in machine learning is that things are way more connected. It is actually not possible to design a meaningful piece of hardware without understanding at least a good fraction of the stack. And by that, I mean from application to software, to compilation, to machine learning models, training, memory, technology circuits, and so on. So the whole thing is much more connected, and it creates very interesting dependencies. Now, that said, not all of these abstraction levels are made equal, and part of it you can actually tell from just agility, which is algorithm and software people are publishing 100 papers per day on machine learning. So if you think that by designing a slightly better piece of hardware over 3-4 years, you can get anyone's attention, that's certainly not happening. So really, the hardware folks and the software folks are in charge, and their models and their algorithms are changing on a daily basis. And if your hardware is not flexible enough to accommodate this, it will have a very, very hard time of being adopted. So that doesn't mean you cannot do any bottom-up innovation, let's say compute and memory and all these things that I'm sure we'll get into. But you will always have to have a lookout and calibrate yourself in terms of what's going on at the higher levels. So in summary, software is king in a way. And the only thing to survive, I think, as a hardware guy, is to stay connected to these people and stay connected to what's going on in algorithms. So that's my initial pitch, and we'll see how people react to that. Thank you, Subhashish.
Thank you very much. Our next panelist is Kaushik from Micron.
Hey, can you hear me?
Yep, we can.
Yeah, thanks. Boris, when I started my preparation thought, all the flow that I prepared over the weekend was completely, streamlined and flowed by your first speech, and we couldn't agree more on that aspect. So, reflecting back on semiconductor self-reliance in semiconductors through AI, as Professor Mitra said, there is a global perspective. There is an Indian perspective to it, and I would like to reflect something on the Indian perspective, right? So. There are 3 stages, right? Who we are as in India, and what ecosystems we have, and what is out there that we got to go and tap, and how do we get there? So reflecting on who we are, math DNA is part deep rooted in India, right? Whether it is way back a few thousand years ago, or as recent as some of the great work that has come from India. And the very fact that the STEM is really, one of the fastest country to adopt STEM and machine learning and AI is India, and that's on one side where it comes to us. When there was a transition to software that has to happen, India picked up the thread much faster than most of the countries. And today, the same trend is happening for AI and ML aspect of it. Speaking from the algorithm and the software side. Hardware side, yes, we are limited. We have what we have, and we are at least 30 years away from a proper advanced nanotechnology fab. But having said that, our contributions to the design world is over 40%. So we are getting to it. As you rightly said, Professor Boris, connecting this hardware and the software is going to be the key and vital aspect of it. So looking at what is out there in the market, if we reflect, this is the third wave, I would say, on the design and the engineering front that India is seeing. 95 to 2005 was the first wave where we did a lot of low-end CAD, CAM, CAE, computer-aided engineering, and few other aspects of it. And that is when when India was peaking up in its software, right? And people working on Y2K, and it was changing the world. The software was changing the world, how it is. But even at that time, India had the CDAC centers and few other efforts through MIT, Ministry of Information Technology, where we were actually doing low-end design engineering world. Past 2005 to 2015 was the second wave where there was more of consolidation, more of acquisition, and a lot of companies abroad started investing in India. They started looking at India beyond BPO or beyond normal software roles, I would say. And that sets the right pitch for us to be here for the third wave between 2015 and 2025, because by 2025, the design field in itself will be more than $100 billion worth. And India is perfectly poised to take a large pie out of it. So This is out there. There is a market that's waiting to be tapped, and we have a largest, I would say, population, which is youth and which is tech savvy, and an increasing adoption in social media platform is a testimony that, and also the number of handsets that are selling in India, that people are tech savvy in their own way. So when it comes to technology adoption, we are not very far. We just have to find the right use cases for the existing technology. On one end, we should create new technology. On the other end, we can be a little more innovative in finding more use cases for the existing technology, and this would tick all the I's and cross all the T's. Having said that, the third part, right, how do we get there? If we reflect back on the Indian ecosystem, there are three things that are very, very vital. One is the academia, industry, or research, right? Can we have a more IP protected and more little open-minded? We can generalize some of the business problems and work with academia. If you look at Micron, in India, what we started is URAM, University Research Alliance of Micron, where we brought everything under a framework, and whether it is a funding for research problem or protecting the IP, we are routing it through that. So industry, academia, research has to go beyond robotics, beyond UV, and beyond a simple ML problem. Why not verification, validations, right? Formal methods. There are companies, there are academic institutes which are specializing in formal methods, but most of them had to leave abroad for better opportunity because there is no scope for them to execute them here. So one is the industry, academia, research. Second, what we need is the framework, and government with our Atmanirbhar coming up with the right framework that needed to put this. The whole idea is not to recreate things. It is about connecting the dots in the right way, in a more innovative way, can actually get us there.
Thank you very much, Kaushik. Yeah. So our next panelist is Sambit. Sambit, go ahead, please.
Hi, Subhasis, can you hear me?
Yep, perfect.
Oh, okay, yeah. First of all, it's a great privilege and pleasure to be part of this very distinguished panel. And I was very impressed with Professor Mishra's talk, and I was just thinking in my mind, hey, can gallium nitride be utilized for this AI and ML? So, coming back to Boris, I think you pointed out correctly, today software is playing a big role, and software is playing a big role because there are limitations in hardware. But software is not going to be good enough to scale to the demand what AI and ML needs are. Okay. And if I look at it, the machine learning or AI, we are trying to mimic the human brain. And human brain is a very complex piece of hardware. It doesn't need any software. It can learn itself, it can infer, it can process itself. It doesn't need a lot of software. So that means our hardware should get there to be like the human brain. Unfortunately, it is not today, it's not there yet. Today, the human brain has around 200 billion neurons and around 32 trillion interconnections. The best ML hardware, I would say, is around 500,000 neurons and maybe 10 million interconnections. That's not good enough. That's not good enough. So that means something has to be done in hardware, something disruptive, something maybe, I don't know, maybe gallium nitride, maybe quantum computing, something has to be done, okay, for us to. Software will not just take us there. We have to invest in hardware. The other challenge I see is that today, again, for the right reasons, because this is such a fast-growing field and that multiple players are attacking this ML indifferently through CPUs, through GPUs, through FPGAs, custom ASICs, and each of them has its own complexity, own software, and things like that. But that's not going to work. I think we have to figure out a way how do we consolidate things. If I look at when we started the PCs or the networking, there were one or two companies like PC, Intel, and Microsoft. They pretty much led the way, and the whole industry rallied around them. So in ML also, I would say that we identify one or two companies who emerge as the leaders, and the rest of the industry, it rallies around them. Because unless we address the hardware piece, I don't think we'll scale up. And the third piece of the information is that today the AI applications, the amount of computing demand they have is doubling every 3 months. And Moore's law can only provide double the computing in 2 years. So that means AI and ML is a different beast, and we have to address it together. I believe India is playing a big role. A lot of companies are working on AI ML, but I would say something disruptive needs to happen in order to. And today we are not even 1% of the human brain, and there's a lot of things to do. A lot of things to do. So I would say the industry consolidate, and we rally as a one industry and focus on bringing in disruptive technologies to build or to meet the computing demand. And of course, it has to be supplemented with the right amount of software. Thank you.
Thank you very much, Sambit. Okay, Sanjay, you go next.
Okay, so I'm assuming you can hear me, right?
Yep.
Okay. So, like Professor Boris also mentioned, right, that the silicon itself or the hardware itself may not be sufficient. Using Sambit's analogy of human body, the hardware is, or the semiconductor portion is just the skeleton. That cannot be self-reliance. If you want self-reliant body, you need to put in enough material, enough other things also, right? So if you want to talk about self-reliance, we need to look at several other things: the algorithms, the computer architecture, the IP, the software stack, etc. That's one thing. The second thing is we often talk about self-reliance in Indian context, etc. But how important is it to be self-reliant? Even if you look at IT sector, right, which has been where India has been well established, assuming that the execution and the architecture and those side we are self-reliant, we are heavily dependent on other geographies, at least for the market. Right? So trying to be very arrogant in terms of being self-reliant, that won't work. We have to be self-reliant more in the humble sense, right? What is more important is to identify pieces of the solution where we can bring in a lot of value and has to fit in with the rest of the ecosystem rather than saying we'll be self-reliant just by ourselves. That being said, right, coming specifically to the topics, I will take a lot of names. These names are not to endorse any of these companies, nor do they necessarily work with Xilinx or don't work with Xilinx. Right? These are names just to give an idea of the variety in the ecosystem kind of thing. Right? Now, coming to the application side where we are doing the best, we as an Indian ecosystem is doing the best. If you look at even in the application side, the majority is around the video analytics, video processing side of things. Within that also, if you go slightly deeper, you will find most of it related to traffic pattern analysis, crowd pattern analysis, number plate recognition, face detection, face recognition, right? Pretty much these areas only. So these give us applications like intelligent traffic monitoring, toll collection, traffic violation, enforcement, etc. kind of thing. Extend that a little bit to surveillance and monitoring, and you are now talking about pretty much what is called smart city. Most of the usage of smart city are more or less in this area kind of thing. Now we have companies like Uncanny Vision, Seed at Trivandrum, Vihant at Noida, companies like Video Analytics, etc. On surveillance and monitoring, you can have things like small, your peripheral apartment complex, your perimeter security kind of thingy. You could have things like social distancing kind of things these days, or you could extend it much broader to say border security, where now you have things like Bell kind of thing, Bell kind of companies. Now, if you go out from video but still stay in the world of image processing, we are dealing with healthcare kind of applications where we have Spline AI, Cure AI kind of companies which look at either the X-rays or CT scans and try to do anomaly detection, try to predict heart attack probability, even try to predict probability of readmission, rehospitalization, etc. Right? ISRO is at the other end of satellite image processing where you are dealing with large geographical areas kind of things. Then we have smart detection in retail, theft detection kind of thingy, where you have companies like Make Computing, which are US-based companies but have significant intelligence. So all this was just to say that in the area of applications, we seem to be reasonably well covered, at least on the video and image side of things. Right? There are several other things where we may not necessarily have been very high, but these areas we are very high. Then Sambit also mentioned about the importance of hardware, right? So all these applications are good and fine, but we need to have hardware systems on which all this is run. We seem to be reasonable here. If you come to the middle level of hardware, we are assembling the systems. Okay. There are companies like iWave Systems, which have products like Corazon.ai. These kind of application systems can do live video analytics and have up to 8 cameras feeding in. Then you have companies like L&T Infotech, companies like Wipro, which are doing a lot of system integration work kind of thing. Right? So again, all that says that the assembling of hardware system also we seem to be reasonably well kind of thing. Now let's come to where we are in terms of awareness. So here we are a mixed bag. If you see STPI Bhubaneswar, they did a smart city hackathon. Excel Point is one of the supporters. Swadeshi Microprocessor Challenge is another one which is being done by SMD, which has been done by Ministry of IT, Electronics and IT. What we are lacking in awareness is, for example, if you look at SMDP 2.0, there's a lot of focus on VLSI, but what about AI and ML? Now, the other thing that happens is what we need to do, experiment with the low-cost architectures, acceleration architectures. Professor Boris probably mentioned about all these algorithms, new algorithms changing very quickly, right? If you stay with a fixed architecture of hardware, that will not be able to utilize those changing algorithms that efficiently. So you need hardware which is adaptive. So you need low-cost acceleration kind of thing. So if you want to develop skills in the hardware side, that's an area we need to work on.
Thank you. We'll come to that. Hey, Sanjay, thank you very much. Okay, so hey everybody. First of all, a big round of applause to the panelists. Okay, they stuck to time and proved you did a fantastic job. So now is the time for the audience to ask questions, right? And like you guys, I have to say, the panelists, you guys are too nice to each other. A panel cannot be successful unless there is a war there, right? So that's what I'm expecting.
No worries, we'll get there. We'll get there.
Okay, we'll see. Okay, thanks. So what I'm going to do is I'm going to start off with a bunch of questions, right, as an icebreaker. And in the meantime, really, I want the audience to ask questions. So, like send us the questions and your questions will be asked. So let me start with the first one. So Boris, I heard the big news that you have been hired as the AI advisor for the Indian Prime Minister. So, so what are you going to tell him, right? I hope you're not just going to say, you have to do everything in a software, hardware, architecture, like that's boring. So what's going on there?
Yeah, well, as an academic, I am, of course, obliged to tell him to empower universities, because the university is where you find the right level of agility to really tackle this problem. Per my previous discussion.
Go ahead.
And, if you actually look at the US and you look at who are the key innovators in this space, they're not people like me who did their PhD 20 plus years ago. They're younger folks. And so the universities are actually the breeding ground for this entire wave as it continues.
Good. So anybody wants to disagree with Boris? Any counterpoints? Guys, don't tell me you guys all agree. Okay, then it would be the most boring people in the world.
No, that's a good advice to Honorable Prime Minister, but you should not limit it to universities in India only. There's a lot of good research going on in US and other countries, so he should expand his network and tap into universities worldwide.
That is all said and done, but do we have a system in place which protects the IP, right? If you look at my patents, I'm still going filing it in Taiwan and USPO. And Indian patents, is it strong? Is it also has a legal bound to it, right? So ask them to protect the IP. People will start investing in it.
Yeah, Kaushik, I somehow disagree with you. This ML stuff is so big and so demanding. I think we need to come together as one world. Okay. I think we have to figure out ways how to get around this IP protection and all these things. Otherwise, we'll not solve to the demand that is there.
That is exactly the point. Yeah. We will do our part. Let them do their part.
Yes, the best hardware is not even 1% of the human brain right now. So if you have to, yeah.
That's good. Sanjay, did you have to say anything here?
Yeah, I am aware of Kaushik's opinion on this IP protection business, right? But I don't correlate that with if IP protection is such an important component or need, how is China showing so much improvement on AI, right? Their IP protection is not supposed to be very well-known kind of thing. So
It protects themselves very well. That's the key.
Let's not get there. Anyway, so here's the thing, right? Boris is going to be the advisor to the Indian Prime Minister, right? So the audience, please send your inputs, and we would like to discuss that, right? By the way, this is not an official thing. I made that up. Okay, make sure
Yeah, I wish.
So don't congratulate him on LinkedIn tomorrow or today.
Okay, but I would be very happy, if the Indian Prime Minister hired Boris. Okay, so let me take the next question. And audience, you need to ask questions. Okay, so if you were my class, I would just stop here and I would say I'm not going to proceed unless somebody asks a question. Now I cannot quite do that over here, right? Because I don't exactly understand how this this system is working. So I'm proceeding, but at some point I will just stop. Okay, unless somebody else asks a question. So in the summit, you asked you brought up the point that about this whole 1% of the human brain business, right? Now you know that there are these two camps, right? One camp says mimic the brain, and the other camp says we don't build flying aeroplanes. So what's your take on that?
Well, I will definitely look forward to any research, anything that says that okay, we can build things better than the human brain or a different way than the human brain. But all research today is pointing towards how do we mimic the human brain. And there are two types of things. I mean, you have your conventional digital neural networks, which process some stuff every clock cycle. They're synchronous designs, and but that's not how human brain operates. Human brain operates it asynchronously. It is discretely, based on discrete events. And there is some research going on there, which I called as spiking neural networks. Even Intel, you have one chip called Lohi, which is tries to closely match the human brain in terms of the discrete event based, asynchronous discrete event based. And with that, that's, I would say, one step closer because you save a lot of power, much faster response, things like that. But I would say again, today we are at the infancy of this whole thing.
So who is going to ask Sambit the flapping wings question?
Yeah, I can maybe ask something.
Okay, I mean, the flapping wings question, right? Go ahead.
Well, I am not against looking at the brain, and I actually do it, right? Just like Subhashish, I'm involved with our brain initiatives and so on at Stanford. But what you learn when you really look at the brain, or our understanding of the brain, is, for example, that we have absolutely no clue, not the slightest bit of a clue, how memory is organized in the brain. And so I do not understand how you can build a brain-inspired architecture when you do not know how memory is organized in the brain. So just saying that there seem to be spikes somewhere in the brain is, for me, not a brain-inspired system. It's really maybe 0.5% of brain inspiration that you take there.
Yeah, but then Boris, the scientists say that we have only extracted or using only 2% of the brain, right? So if we can get a pie out of it, I think we are there. See, if you look at the AML...
I let them speak for themselves. I'm not sure that's true for me.
But if you look at the AML space, it is pyramidal, right? And the autonomous system and self-learning is at the pinnacle of it. But there is a whole base where you can actually train and look at the use cases, innovative use cases that can provide value, accelerated decision to the people to enrich their lives today, right? While if the function requires it to be at the top, focus at the top, but there is a whole pyramid base that is available waiting to be explored in the AML space, where it doesn't take a lot of compute power, or doesn't take a lot of dollar resources to do that research. So that should also be there.
Hey, Kaushik, you brought up training. So is training going to be at the edge in the cloud, or what the heck?
I mean, training at the cloud is the bread and butter. I cannot take that away from it. But can we? It helped us so far, but it is not going to take us to the 2025 wave that's going to come forth, right? We can what today they do is build it at the cloud and then implement it at the edge. But we can retrain it at the edge with low latency and high bandwidth memory, right? That's something can be the way forward, because if you look at any asset monitoring or any target at the nature of the data that it throws out is not going to change drastically at all. But there is a state change that is inherent, that is maybe because of progressive degeneration or because of influencing from the external factors, that can be retrained at the edge. It doesn't have to take the whole cloud to do that retrain part. So the way forward should be, you can build it once, but you got to learn it train it itself at the edge with the delta. That will be challenging.
So you come from a company that builds hardware foundations. So what are you doing about all this?
So if we look at the way the data and its problem statements have evolved over these years, every application is different, and everything is kind of in its variety, the way it brings in. There is a diversity in data. There is a diversity in the analytics or thought process or the business value that it brings in. Most importantly, gone are the era of a rigid or a single high performance computing system in place. Today, there is a variety. If you look at the convergence of AI, ML, the big data, and all the modeling and even simulation, everything is converging. So the way forward is heterogeneous system. Can this system be repeatable, scalable, and reliable across the spectrum?
But wait a second. You come from a memory company, right? You build memories, and you're talking about heterogeneous systems. I thought that and there's Intel sitting on the other side. You got memory, and Intel got logic, and you guys don't talk to each other really, right? And aren't you guys on all this the PCM stuff? So it seems like things are going the opposite way than what you're saying.
But if you look at what Micron provides, right? I am speaking for Micron, speaking for myself. What Micron does is essentially.
Samit can talk about Intel.
Maybe Intel and Micron should merge. No, I'm just...
Oh, okay, that's the other news, right? On LinkedIn tomorrow.
No, yeah. Please don't say that.
No, by this time it would already be viral in LinkedIn today.
Now, who gobbles up whom? That's the question, right?
So if you look at the broad portfolio that Micron provides today, we create systems that can fuel the analytics and the next way of AI that's coming in forth. So in compute memory and real-time response to whether it is an ADAS system or an automation, or whether it is a chip-a-geddon that's happening while the shortage of chips in the world, all these can be addressed. And in compute memory and high bandwidth memory is the way forward. And
okay, we'll come to that. Hey, there is an audience question for Boris. What is the role of agile hardware design in AI/ML applications development?
Wow, this is a tough question. I
would say a good audience. They're asking tough questions. That's what they're supposed to do.
Well, agile hardware development is actually something very new, and the main idea is that people are saying, hey, in hardware there's little to no reuse and no abstraction, whereas in software, I can, download a bunch of modules that other people have written, and within 3 minutes, I can throw together a meaningful application. And this is not the case in hardware design. And so people in academia are working on developing design flows for agile hardware design. That would be fantastic for ML, because we could finally better match the rapid design cycles. But I wouldn't go as far as saying there is already a role. I think it's a much bigger problem that goes beyond AI.
But Boris, there cannot be any agile hardware design unless the design verification problem is solved. In software,
that problem would have to be solved. You can roll out a bucket
software and fix it. Go ahead, please. Yeah.
Yeah, that would have to be solved. You can talk to your colleagues about that who are working on that, right, in your department. So,
that's good. That's good. So Boris, continuing, since Kaushik brought up, the I word, right, in memory. So what's your take about, and I'm starting with Boris, but I'll actually go to everybody else, on this one, analog versus digital implementations, inside memory versus right outside memory, right? New technologies like RRAM, PCRAM, 3D. So what's your take on all that? And next, Sambit, be prepared. I'll come to you next. Go ahead, Boris.
Yeah, I'll keep it relatively short. I've looked at many of these things over the years. And I would say as a summary statement that the jury is still out whether any of these things will make it. You can definitely derive advantages by microscopically looking at, say, a compute in memory unit, and you claim a 10, 20x improvement, but oftentimes we don't go far enough to validate if these improvements actually translate all the way to the system. And so research that is currently underway is trying to establish that in a much better way. And I think we have to await these results to really be more intelligent about it.
Sambit, your take, all these new technologies, RRAM, PCRAM, 3D integration, new forms of other kinds of, chiplet integration and so on?
Well, we're all trying different methods of how to do much higher processing with much lower power. And today, one of the big bottlenecks is the power due to memory access, whether storing things in the memory or accessing to the memory. So that's why all these new technologies, whether in compute memory, near compute memory, high bandwidth memory, or all this analog stuff is coming up. I think the memory technologies, I would say, are showing good promise, and I think logically it makes sense. The analog stuff, it will take some time to have a good proof of concept and see really how it could, because analogs are still a research area, and it takes several iterations to get all the analog stuff right. So I would say that's a little far out. But these memory technologies, I would say they will do pretty well. And there's a lot
but what good is a memory technology? You have a lot of good memory technology here at Stanford, and then you have a lot of good logic technology sitting at San Francisco, and all the time and energy spent on the traffic between in Palo Alto and San Francisco. So what are we going to do about that?
Well, as I said, if a good logic company, a good memory company, and a good university, if we all join hands, I'm pretty sure we can do something good. And it's just that we are looking at the problem, each of us, in a very silo way. And we talk at a very high level. So I think there are opportunities between Stanford, Intel, and Micron to come together.
Okay, so you went on record on that one, right?
Yeah.
Okay.
Yeah.
I'm going to take you on that. Okay.
Yeah. Sure.
Is the recordings available?
And you do not want to work with Santa Barbara and Purdue?
Well, if I do not know how much research they do, but
oh, that's brutal. That's brutal. That is brutal.
Okay, guys, let's end the topic a little bit. So, hey, so let's go back to the Indian context, because there is a notion of self-reliance. So, there are some questions, on the chat, like by audience. By the way, the audience is actually sending out really great questions. Thank you very much, the audience. Highly appreciate that. And, so why is India lagging in all this? Even if you think of the design ecosystem, forget about the technology fab and all that, right? So why are there no fabulous companies in the AI/ML space when there are 20 to 30 companies in the non-AI/ML space, for example? I mean, these are fabulous companies, right? So why is it so?
I wouldn't totally agree with it. I strongly disagree with that, because
okay, so that's numbers. Okay.
Yeah, India is contributing to 40% of design output, right? And then we have close to more than 70% of contributions on the software side. All we need to do is just marry them at the right intensity. And most importantly, we got to identify the market to have an innovative solution. It doesn't really have to be a 3 nanometer technology solution, right? What can be achieved with a much low end chip? We call it a low end high tech for chips. That should be the way to go.
Yeah. Well, I partially agree, if I may say, Subhasis. Okay, so I partially agree. I think we are doing well in silicon design in some of the big companies like Intel, Qualcomm, Micron, NVIDIA, things like that. Of course, we're not doing that probably as good as Silicon Valley does. Now, the primary reason is that Silicon Valley has maybe a 40-year history of doing semiconductor design, and India probably has maybe 15 or 20 years. Okay, so that's one thing. The second reason is that Silicon Valley has a lot of good tie-ups with universities, and in India we need to do better in that. And the startups also need a lot of funding, which is a little difficult to come by in India. But it's steadily increasing. I think the other thing to look at is that India is definitely excellent in software and software technology. So, and AI, ML, at least in current form, needs a lot of good software expertise, and I think India can play a big role in the software piece of it. While in hardware, it will go at a steady pace, I would say.
So, there is a related question. Yeah, go ahead, please. Sanjay, you wanted to say something? Go ahead, please.
Yeah, I'll just add one more point, right? All these points are very valid. There's one more point. Conferences such as this actually act as sometimes dampeners to such initiatives. Okay, this seems very bad. In such conferences, we all talk about high-end stuff, but in reality, there's a lot of low-end stuff that can be done, right? When people come to such conferences, they think that unless they can have multi-billion dollars, multi kind of thing, right? They cannot really go for it. On the other hand, we have seen a paper published by, say, Nanjing University of Aeronautics and Astronautics as late as just about last year, few months back, where they took a very low-end FPGA and used that with a RISC-V based coprocessor to get 6.3 times acceleration for convolution, right? So what I'm saying is there's a lot of space for relatively low cost, low end work using existing programmable devices, using existing coprocessors to come up with solutions. Somehow we don't even think of those. We only think unless you go into the high end cutting edge, nothing will happen. It's not a 0 and 1 business. There's a huge scale in between, right? Which we need to also try to tap into.
That's a good segue to my next question, Sanjay, that you brought up. So, you represent an FPGA company, right? It seems like, something funny is going on with this FPGA business, right? On one hand, GPUs, they say, they can solve everybody's problem. There is no need for all that. The FPGA companies are themselves getting gobbled up by the big giants, right? AMD, Intel and all that. And now there are these CGRAs. They're the new kid, like from the, an idea from the 1990s, but now they're the new kid, like rediscovered, right? Reinvented. And they're the new kid in the block. So it seems like, would anybody care about FPGAs, 10 years down the lane?
Yeah. So we do encounter some these questions once in a while, right? Why even FPGA is relevant? And the fundamental reason is anytime you read a textbook, FPGA is defined as CLB and configurable logic block interconnect. That's all FPGA is defined as.
But a true FPGA has what?
But the FPGAs have changed a lot, right?
That's right.
That's only the classical definition in textbook only, right? There's a reason why AMDs and Intels are gobbling up FPGA companies, right? We talked slightly about processor companies and the memory companies not talking to each other, right? And when they want to talk to each other, then you feel that, okay, they don't have a future, right? We are talking to each other kind of thing. Anyways, if you look at some of the modern FPGA devices, let's say ours, what we call as a Versal or AECAP, right? Adaptive Compute Acceleration Platform, that has specific core array for AI, which we call it AI engine, right? Specifically for AI applications. And the reason why we call those are specific for AI applications is because they have memory embedded with the core, right? The memory sits right next to the core. This was a point that probably Sambit had pointed out. We are talking about around 12 MB memory seated right with the computational core. We are talking about massive parallelism, around 400 or so cores lying up in an array. Each core can do up to 7 operations in parallel, right? We are talking about several gigaflops of operation per second, okay? So this is all still FPGA, though my CEO doesn't like if we call this as FPGA, right? We have had competitions organized by one of my colleague Radhika at IIT Kharagpur, at IIT Mumbai, at DAC, where students used FPGA devices, and I'm not even talking about high-end FPGA devices like ACAP, the low-end FPGA devices, to deal with a high number, and I can go into specific numbers kind of thing, around 26 frame per second image processing, image classification kind of thing. And when we went on a per watt basis, we did much better than any known GPU result. We were around 5.42 frame per second per watt.
Got it. So you're saying, hey, FPGAs are not your textbook FPGAs. Fully agree.
Exactly right.
And FPGAs are providing the infrastructure also to be able to run and accelerate AI ML, for example, right? But if you look at the value, for example, if you look at a company like Samba Nova, their claim is that they're doing so much better than FPGAs. So maybe FPGAs are good, but maybe they're not good enough.
And again, I have to look at specifically this specific company what we are talking about, right? But the GPU versus FPGA, a lot of research papers have been published, and there it has been established. And these are not Xilinx papers; these are papers by our competitors, right? First for Altera and now Intel PhD, right?
So Sanjay, I have a question for you, and I agree with you that FPGAs are good for providing quick solutions and pioneering some stuff. They're definitely good. You said FPGA is better than GPU. So then why GPUs are not getting implemented in FPGAs? They can do it very fast.
So one place, Sambit, where we have a slight disadvantage is what you had mentioned slightly earlier, right? The reason why we are behind Silicon Valley is ahead of us by 40 years or 20 years, right? GPUs got into this business much earlier than us. So it's not just about the hardware, the whole software stack, right? There we are slightly lagging behind, and we are working towards covering that. Will finally GPUs be implemented over FPGA? Will FPGAs be implemented over GPU, CPU over GPU? None of those things are going to happen, right? Each of these things bring in their own areas of strength, and we all need to talk to each other and deal with and make use of each other's strength, right? Yeah. None of these will get implemented over each other.
Good. I think these are good discussions, and I think we have around 10 minutes left. There are some really interesting questions that are streaming in. I will start with the first one. So Boris started off talking about academia in general, right? That and then there have been some sprinklings of academia here and there. We did not really hear much about what's going on with AI/ML hardware. I mean, in Indian academia. Can somebody tell us about it? And I think we should have a good discussion about that. And there is a related question from the audience, which has to do with investments. I think these are related questions. So let's start with the Indian academia and AI/ML hardware research. Maybe you can tell us about that. Everybody's mum, everybody's quiet.
Yeah, that gives you the answer, right? That none of us are aware of any major work going on in AI/ML hardware in academia.
Is this really true?
No, there are pockets of research happening, but definitely not as pronounced as you would in US. And I think different companies, including Intel, we are looking at how do we kind of invigorate the academia, and partner in certain aspects of AI and certain aspects of 5G, because AI and 5G combination is quite deadly. So we are looking at that, and there are some professors who have started engaging with us, and hopefully the next couple of years we'll see much more active academia industry collaboration in India in AI, ML, 5G areas.
And also,
what's your take? Yeah, go ahead.
Yeah, and also, very recently, Sanjay, our CEO, had a talk with Ravi Shankar Prasad, the ministry, who heads the ministry at the central level, and also with KCR and KTR at the state level. So there are efforts to have a center of excellence in memory, and some of these programs are obviously part of it, that needs to come up. As I said, there are other areas within this. It doesn't really have to be an advanced 3 nanometer technology. There are so many low-end, low-hanging fruits that can be derived out of it. And the goal is not to mimic the Silicon Valley. We will fail terribly on that. In the Indian ecosystem, what we need to do is to identify innovative use cases on the low-hanging sector, which will enrich people's life. And that's the mission for Micron as well. So things are happening, but nothing that we can kind of go and publish it types.
I'm really shocked about this, about this whole Indian academic thing, and I'm actually very sad about it. Basically, somebody says that there is a Robert Bosch Center on AI at IIT Madras, and then brain research at ISC.
Yeah. IIT Madras is probably the only one where I keep on hearing the name once in a while in terms of some research, and especially in the context of 5G, along with work with some of the industry. Now, When Sambit said that they are working with some professors, I don't know whether he talked about some other universities or only IIT Madras.
That is also, Professor Mitra, that is also partly due to the fact that the amount of focus the corporates have in a technical conference vis-a-vis amount of participation we have in an academic conference. Right.
Okay. So there is a related question. I'm just bringing up that question because I think it's related. Somebody from the audience made this point that let's say that we want to develop academic institutes in AI, right, in India. So then the government has to come big time, and put in money. And the assertion of this person is that they think that considering the COVID impact, the governments are not in a position to put in a lot of money. So what's the alternative? How much will the industry invest? And they think that the industry is not going to invest much, and that's the end.
Yeah.
So, what do you guys think? Well, that's a serious question.
Yeah. No, so that's a great question, and I think we as companies, we also have a responsibility, to fund some research, to sponsor PhD students. Actually, in my group we started some of those programs, and hopefully it will start showing some success this year or next year. But it's important that we companies step up and assist the government in any sponsorship, co-research, sponsoring PhD students, things like that will definitely be very helpful.
At Micron, we have the URAM framework where government bodies are part of it, be it an advanced computing system or MIT, lab, Ministry of Information Technology labs. And we are also partnering with the state and, routing the funding through this. And more than 12 top tier institutes in India are part of it. And if you look at it, predominantly it used to be engineering focused in the early days. Now the focus is beyond engineering, and we have some of the math institutes, Chennai Mathematical Institute, part of the URAM framework. And we are also slowly exploring other options where verifications, validations, formal methods are eventually going to become part of it. So the effort is happening. But two things is needed. For us to accelerate it, we cannot go and dug up space and then plant a university saying that this is going to be the center of excellence for this. All we need to do is connect all the dots.
It has to be organically. It has to happen organically.
Yeah. Organically.
Yeah. Hey, our program chair is somebody wants to say something? Go ahead, please.
Yeah. What will help us is that because in US, academic and industry has collaborated for a long time. It will be great for Subhash, yourself and Boris to share with us some good learnings or good things that we can implement in India.
Sure, we'll be glad to. Hey, our program chair has a question, and since the program chair is sitting here, I would let him ask directly rather than reading his question.
Hey, thanks, Shubhashish. So, question is, has to do with the fact that even if we do achieve self-reliance in AI from a technology perspective, right? The hardware and software, whether it is, the chip level, system level integration, software, whatever it is. But are we really ready from a regulatory standpoint, right? I mean, what happens if just getting a technology solution is not sufficient, to be truly self-reliant in something, right? Sure, we can have a good system, but as long as if it doesn't see the light of day because of other challenges, regulatory or otherwise, then there's really no point to it.
Right? What do you mean by regulatory?
It could be liability, for example, right? There's a company that builds an AI system, let's say, right? You have an AI system that is built and deployed, and let's say it goes horribly wrong, right? Who takes blame for it?
Hey,
we have a set of framework.
The program chair is the most important person in the conference, and this is the last question. Who is going to take this question, and then we'll close the panel.
Okay, I'll just start if I may say, okay, and it'll be good to hear from others. I think this whole AI, ML, regulatory, security, privacy is a big open and a big research area all over the world. So I don't want to undermine that. It's a big open. Now, in India context, at least I know that our Honorable Prime Minister, in his drive to a $5 trillion economy by 2025, he is very open and very supportive of any technology solutions we build, and will definitely help in managing or solving some of the regulatory or the bureaucratic challenges. So we have a lot of programs with the government, and it has been very smooth, I would say. So that's helpful. But in the global world, in the AI, ML, I would say everybody is concerned about privacy, about security, about many things, and how it needs to be regulated.
Anybody else wants to take this?
Yeah, I want to say that.
Yeah, go ahead.
Go ahead.
Yeah. So essentially, as I said, going back to the framework, right? How do we get there? This is one of the key things that needs to be in place. Regulatory in terms of what is a purposeful use case that is possible, right? Human cloning has been regulated not to happen. It is possible, but we decided as a humanity we will not do that. Similarly, there has to be regulations in terms of the use cases. There are regulations in terms of this ease of doing business. I think with Atmanirbhar and Make in India effort, Digital India, and 5,000 smart cities are coming up. The work is happening, but the thing is that it is not talked at the media because it's not going to increase their TRP rating. Right, so work is happening at the grassroots level, and few technologists and few companies at certain level are aware of it, and there are talks to have maybe a testing solution from India. We may not have a full-fledged fab, but there could be an advanced testing solution, a packaging solution coming out of India. We may not ape Silicon Valley, but certainly a Taiwan or a mini China is definitely possible. That's coming our way.
Good. I think that on that positive note, let's close this panel. Let's thank the panelists. Boris, I have to tell you, wherever you go, these analog questions don't come after you. There's a question about ADCs and analog FPGAs, but I will spare you on that. Okay. But hey, I have to say the audience did a fantastic job. So first, let's give a round of applause to the audience. They asked terrific questions. Okay. And then the next round of applause is for the panelists. Guys, you did a fantastic job, okay? Thank you very much. This is the end of the panel. Thank you for your attention.
Thank you.
So thanks a lot on behalf of the conference and the VLSI Society of India. I thank each one of you to sparing your time today. I'll request admin to bring up the a virtual token of appreciation slide here. We'll be shipping a physical one later. So I'm just curious to know, though the panel is over, we already have AI in India. If you see INDIA, so we have an AI, but in reverse, okay, from the very one day. So how do we, make it on the right side? And, when can we expect, a Mangalan of AI, indigenous Mangalan of AI coming up? So with all this, thought-provoking, I would say interesting deliberation. I think we'll have something better, something advanced by the next year when we again meet for this conference. So I thank each one of you. Sorry, Subhashi?
I said in person, right? Next year it's going to be in person. In person,
right? Certainly in person. And probably maybe a hybrid so that we can have more of the international participants coming in without any expense of time and money.
You have to try Indian food and travel, so don't do hybrid, do it in person.
Yeah, so Maurice, I see coming along with Subhashish next year at VLSID.
So there you go, Maurice, you just agreed to come to India next year for the VLSI conference.
We'll have to see about that.
Yeah. So I remember last year there were a lot of hand-signed notebooks, books of Rabbe we gave to audience, and we are looking forward to another container of books by Morris for the next year.
Okay. Yeah. Okay. Maybe
so that motivates people to come down here.
You're going to get rich by giving those autographs.
All right.
Yeah. But those are the books which are self-sponsored, Morris. Take a note of it.
Okay.
So with this, let us conclude today's session. We'll break for the 3 panel sessions, and we'll resume by the keynotes after an hour down the line. Thank you so much. Really appreciate your time and all the great views. Thank you.
Thank you.
So with this, we'll conclude this session, and we'll meet after the 3 panel sections after a break of 100 minutes from now, and we'll continue with the next keynote. Thank you. Have a great day. Enjoy the conference.